Hello, this is the 24th video on my Multivariable Calculus course. In this video, we're going to talk about parametrized surfaces. To parametrize a surface, we need two parameters. Why? Because a surface is a two-dimensional object. So to parameterize a surface, you need a parameter for one direction and another parameter for the other direction. And usually I denote those two parameters in general by U and V. So in this video, we're going to talk about a few examples on how to parameterize surfaces. Parametrizing surfaces is a very important concept since we're going to be using this parameterized surfaces and parameterized curves in evaluations of surface and line integrals in the later videos. Okay, so we'll do a few examples in this video. The first example is parameterize the surface given by z equals x squared plus 2xy that lies above the square in the xy plane, that the vertices are 0, 1, 0, 0, 1, 0, and 1, 1. So how do we parameterize this surface? Well, let's first look at the parameter region. So the region on the xy plane is a square like this. So it is from 0, 0, 0, 1, 1, 0, and 1, 1. So this is our parameter region. So how can we parameterize this surface? Well, we could say the x-axis, the x-coordinate is just x. The y-coordinate is just y, and the z-coordinate is evaluated by x squared plus 2xy. Now, any parameterization must come with the limits of parameters. So what are the limits of x? Limits of x from the diagram are 0 and 1, and so are limits of y. So this region is a vertically simple region, and it's also a horizontally simple region. So we could parameterize it this way. So let's look at part B. The surface given by z equals f of xy with xy inside this disk. So if we look at the parameter region is on the xy plane, and it is a disk of radius 1. So how do we parameterize this surface? Again, this is the graph of a function. There are two ways of parameterizing this surface. The first method is something similar to the one above. So r of xy equals x comma y comma 2xy. Z is equal to 2xy. That's what is given. And then this surface, this region is a vertically simple region. So we could say y goes from bottom to top. So what is the bottom of this disk? The bottom is y equals root 1 minus x squared because the radius is 1. And then the top is y equals root 1 minus x squared. The bottom has to have a negative sign. So limits of parameter are going to be negative 1 minus x squared in square root and positive square root of 1 minus x squared. And then the limits of x are from negative 1 to 1, because this is negative 1 and that's 1. So this is one parameterization, or we could do it using polar coordinates. So how do we use it? How do we use polar coordinates? We could say, well, r and theta, or technically it is in fact cylindrical coordinates. We could say r and theta are our parameters. So the base would be r cosine, r sine, and the height would be 2xy. So it would be 2 r cosine theta r sine of theta. And of course, I'll have to specify the limits of our parameters. So r is between 0 and 1 because it is the unit circle, and theta is between 0 and 2 pi. So what we got so far um, were two examples that both of them were graphs of functions. So let's look at more examples. The next one is the sphere centered at the origin with radius a, and a is a positive constant. So we have a sphere centered at the origin, and we want to parameterize that sphere. So how do we parameterize a sphere centered at the origin? Well, the best thing to do would be to use spherical coordinates. So, well, we know that rho is equal to a because it's the sphere itself. It's not the ball of radius a. They didn't say x squared plus y squared plus z squared less than equal to a squared. They didn't say a ball. They said a sphere. So rho is equal to a. So that means I can use phi and theta as our parameters. X coordinate is rho, which is a, sine phi, cosine of theta, and then rho sine phi, sine of theta, and then rho cosine of phi. So this is our parameter, but as usual, any parameterization must come along with limits of parameter. Since it is a full sphere, phi goes from the top, which is 0, to the bottom, which is pi. So limits of phi are 0 and pi, and limits of theta are from 0 to 2 pi. So this is the parameterization for this surface. Okay, so next one is another parameterization example. And as I said, this is a very important concept. The first thing we want to do anytime we want to evaluate a surface integral is to be able to parameterize the surface, which is why I have a lot of emphasis on being able to parameterize surfaces. The cylinder given by x squared plus y squared equals a squared. So we want to parameterize that. So let's draw a diagram for this. So the surface looks like this. It's the entire cylinder. So there is no limitation on x. I'm sorry, on z. So how do we parameterize this? Well, this is not the graph of a function. So we could use the spherical coordinates. I'm sorry, we could use cylindrical coordinates. Well, for cylindrical coordinates, radius is a, and theta is changing, and also z is changing. So the parameters are theta and z. So the radius is a, so it would be a cosine theta and a sine theta, and z could be anything. Now again, we'll have to specify limits of parameter. So theta goes from 0 to 2 pi, and z is real. So something needs to indicate that this is an infinite cylinder. You could say z is between negative infinity to infinity, or you could say z is a real number. Next example is another parameterization. Part of the cone below the plane z equals 2. So let's draw the diagram again and write down the parameterization. So we have a cone and it is capped by this z equals 2. And again, it's the cone itself, not the top of the cone, not inside the cone. So let's parameterize this one. So how can we parameterize this? Well, there are a couple different ways of parameterizing this. We can look at the projection onto the xy plane. If we project it onto the xy plane, then we're gonna get a disk. So the top, or let me put it as a projection onto the xy plane. So projection onto the xy plane is going to be x squared plus y squared equals 2, because we had x squared plus y squared, or in fact the square root of that equals 2. So this gives us a circle of radius 2. So this is the projection onto the xy plane. And then because the projection onto the xy plane is a disk, we would want to use cylindrical coordinates. In this case, r and theta are both changing. So we could say r and theta, x coordinate is r cosine, y coordinate is r sine, and z coordinate is on the cone. So what is the equation of the cone? The equation of the cone is z equals root x squared plus y squared, which is r. Now, what are the limits of r? Limits of r are from 0 to 2, and theta from 0 to 2 pi. Again, as usual, any parameterization must come along with limits of parameter. Now, there are other ways of parameterizing this one as well. We could also use spherical coordinates to parameterize this one. I will write down, in fact, the spherical coordinate parameterization as well. So this is the first one. The second method, so this is a different method for the same problem. We could use the spherical coordinates. So let's look at the cone. The cone is z equals root x squared plus y squared, which is rho cosine of phi equals rho sine of phi. So that gives you tan of phi is equal to 1, which means phi is pi over 4. So that means in the spherical coordinates, we would have phi equals pi over 4. Now, what are the limits of theta? Well, limits of theta are again 0 to 2 pi. And what are the limits of rho? Rho goes from 0, which is on the origin, to the plane z equals 2. So let's see what z equals 2 is. Z equals 2 is rho cosine of phi equals 2. So that means rho is equal to 2 secant of phi. So here is another parametrization. So we could use parametrization as rho, phi is pi over 4, and theta. First component is rho sine phi, which is pi over 4, and then cosine theta. Second component is rho sine phi sine theta, so sine of pi over 4 sine theta. And last component is rho cosine of phi. And as we saw, phi is pi over 4. And again, we have to write down the limits of parameter. So theta is from 0 to 2 pi because we have points in all different quadrants. And rho goes from 0 to 2 secant of phi. So this is the second parameterization for the same surface. Okay, so let's look at the next example. Parameterize the surface of revolution, surface obtained by revolving the graph y equals x squared about the xy plane. Okay, so let's do that. So y equals x squared is something that looks like this. And I want to rotate that about the x-axis because they said rotate about the x-axis. So you'll get something like this. Something like this is the shape that you get. Oh, you'll get something like this. So now we want to parameterize this one. So how do we parameterize it? We are going to take a point, let's say point x on the xy plane, and we are going to look at this circle that we have. What is the radius of this circle? The radius of this circle is f of x. So in fact, let me put x a little bit further. So this is x. This radius is going to be f of x. So if I draw that circle right here, you have a circle, and this is the YZ plane, parallel to the YZ plane. One direction is the y-axis, the other direction is the z-axis. So that's like the y-axis, and this one is the z-axis. What is the radius of this? Radius of this is f of x. So how do we parameterize this? Well, we could say y equals radius cosine of theta and z equals radius sine of theta. So how do we write down the parameterization? Well, we could say r of the two parameters are x and theta. So what is the x component? Well, it is just x. What is the y component? It is, so this is the graph of y equals f of x. It is x squared, which is our function, times cosine of theta, x squared times sine of theta. X is any real number because x squared is defined for every real number, and theta is between 0 and 2 pi. So this is the parameterization of this surface. Now, in general, if you are given a um, surface of revolution about the x-axis and you're revolving y equals f of x, the parameterization is going to be x f of x cosine theta, f of x sine theta. X is in the domain of your function, and theta is between 0 and 2 pi. So the last thing we're going to talk about in this video is the tangent plane. So imagine you have a surface, but your surface is given by a parametrization. So you are given by f of u comma v. When you fix your u, you get these curves right here. And when you fix your v, you get curves in perhaps another direction of this surface. Now, if you fix your u and differentiate the blue curves, what are you going to get? You get these tangent vectors. So fixing u, we get r sub v. This is partial of the position with respect to v. And if we do the same thing for the other ones, we're gonna get r sub u, which is the partial of r with respect to u. So if v is fixed, differentiating, we get partial of r with respect to u. And those two vectors are tangent to the curves that are on the surface. So what does that mean? It means, so this is what we just talked about. R of u and R of v are tangent to the surface. So what does that mean? It means if I want to define tangent plane to the surface, I'll have to find the normal vector to the tangent plane by finding the cross product of these two. So if R of uv is a parameterization of a surface sigma, then R sub u and R sub v are both tangent to the surface. Thus, their cross product is a normal vector to the surface. So let's do an example on this one. Find an equation of the plane tangent to the surface of revolution in the previous example at this point. So let's first write down the parameterization that we had. It was x squared cosine of theta, x squared sine of theta, and that's exactly what we got right here. So now we are going to have to find the tangent plane. In order to find the tangent plane, we need one point and we need a normal vector. So we are given a point 1/1/2 and root 3 over 2. We'll have to find the normal vector. So first we're going to find the partial derivatives. 1, 2x cosine theta, 2x sine theta. And then partial with respect to theta is 0 minus x squared sine theta, x squared cosine of theta. Then we'll have to find the cross product of these two. But before that, let's find out what x and theta are so that we can reduce our computation. So at 1/1/2 root 3 over 2, we get x squared cosine theta, x squared sine theta is equal to 1/1/2 root 3 over 2. And what does that give us? That tells us x is equal to 1. So if you look at the first components, they're x and 1. The second component is x squared cosine theta and 1/2. So that means cosine of theta is 1/2. And the last component is x squared sine of theta, which is root 3 over 2. So sine of theta is root 3 over 2. So what does this mean? It means at this point, our x and our theta can be evaluated by these formulas. So 1, 2 times cosine of theta, so this is 2 times 1 times 1/2, 2 times 1 times root 3 over 2, 0, negative 1 squared root 3 over 2, and 1 squared 1/2. So if you find the cross product of these two, we are going to get, so eliminating the first one, so we're going to eliminate these, we're going to multiply those, we get 1 times 1/2, so that's 1/2 minus, so that is plus, and then root 3 over 2 times root 3 over 2, so plus 3, or plus 3 over 2. So that's 1/2, so that's 1/2, and then plus root 3 times that. Okay, so that's fine. Then we're going to eliminate this second column, multiply, we get 1/2, and then the other is going to be 0. And then we have a negative sign, of course. For the second component, you always had a negative sign when you do the determinant. And for the third one, we get negative root 3 over 2. So that's a normal vector to the tangent plane. So now we can write down the equation of the tangent plane from what we have learned before. It would be 1 half plus 1, 2, 3 halves, which is 2, times x minus 1 minus 1 half y minus 1 half minus root 3 over 2 z minus root 3 over 2 equals 0. So that is the equation of the tangent plane. So to summarize, the graph of a function f of xy can be parameterized by r of xy equals xy f of xy. Spheres are often parameterized by spherical coordinates. Cylinders are often parameterized by cylindrical coordinates. Cones are often parameterized by either cylindrical or spherical coordinates. If you rotate the graph of y equals f of x along the x-axis, we obtain a surface that is parameterized by x, f of x cosine theta, f of x sine theta, and a complete parameterization must include limits of the parameter. R of u cross R of v is a normal vector to the surface given by R of uv. And that brings me to the end of this video. I will see you in the next video.